Namaste, Namaste everyone. Welcome to second PUC physics class. We were in radioactivity and nuclear physics, correct? And we were discussing about different aspects of radioactivity. Namaste, decay law, the equations which govern the decay of the number of atoms remaining after a certain time. Half-life, mean life. If you want to remind all the formulas once, it will be like this. The formulas will be like this. N is equal to n naught e to the power minus lambda t. This gives the number of atoms remaining in the sample after a time t. Okay. So n is equal to n naught e to the power minus lambda t, and decay constant is 1 over mean life, or which is also equal to 0.693 by half-life, right? Then what else? Yeah, half-life is 0.693 by lambda. Half-life is that same formula, previous formula. So this is how we relate, how do we relate all the things. Now using these formulas we have to solve the problem. We will go to some problems, and then we will move on to some entrance exam problems also. The problem moves like this. You have this problem in your that PDF sheet. The activity of a sample of polonium atomic number 84, mass number 210, of half-life 138 days is 5 millicurie. The activity of a sample of polonium is 5 millicurie. Find the mass of 84 polonium 210 sample. Avogadro number is so much. So if it has to show this much of activity, if the polonium has to show that much of activity, what should be the mass? Because you know that activity of a sample is directly proportional to the number of atoms in the sample, correct? Therefore, mass of the sample decides how much is the activity, because more the number, more will be the mass, more will be the activity. Activity is directly proportional to n. So we have activity is equal to minus lambda n. If I take activity as r, because we write this formula, dn by dt is equal to minus lambda n. dn by dt is proportional to n, and dn by dt equal to minus lambda n. So r is equal to minus lambda n, where r is the activity. Of course, r is equal to plus lambda n, because r is minus dn by dt, right? Minus dn by dt itself is r, so r is equal to plus lambda n. Now, okay, if you take it like this, now activity is given. So from the activity, you have to calculate what is the number of atoms. From the number of atoms, you will have to find out the total mass of the atom, because you know Avogadro number of polonium weigh 210 gram, right? Mass number is 210. So 6.02 into 10 to the power 23 atoms of polonium will weigh 210 gram. Then how many atoms will weigh so much of gram? Something like that. Now you take the activity. If you know the activity, you can find out the number of atoms in the sample, because lambda is given. Even though now lambda is not directly given, it is given in the form of half-life. Lambda is given in the form of half-life. So how can you calculate half-life of the sample? Half-life of the sample is 0.693 by lambda, correct? If half-life is 0.693 by lambda, that is equal to 0.693 divided by lambda. Lambda is, because I want to use this formula, A is equal to lambda n, or R is equal to lambda n, activity is lambda n. So I want lambda is equal to 0.693 by half-life, that is equal to 0.693 divided by, what is the half-life? Half-life is 138 days. 138 days into, we have to convert it into seconds, because everything has to be done in the same platform. Here what happens is, this is in curie, so you have to convert that curie into becquerel. You know 1 curie is equal to 3.7 into 10 to the power 10 becquerel. That is the unit. You know this is the activity of 1 gram of radium. Okay, 138 into, so convert it into seconds. 138 days, 24 hours, 60 minutes, 60 seconds. 0.693 divided by 138 days, 24 hours, 60 minutes, 60 seconds. So lambda is equal to, we will calculate it first. You take the calculator and go along with me. Don't simply see this problem. Watching this problem is very injurious to health. You have to work it out. So working out of problem along with the teacher is better for health. Yes, an apple a day keeps the doctor away, right? So a problem per day keeps you away from a teacher, because you can crack the exam yourself. You need not have the help of a teacher. So solve the problem yourself now, along with me. So we got lambda. Hope you have got the idea of solving the problem. From lambda you can use activity is equal to lambda n, because activity is given. Only the thing is activity has to be converted into SI system, and then once you know the activity, you will get number of atoms in the sample. From the number of atoms you have to calculate mass, because Avogadro number weigh this much of mass, 210 gram. Okay, lambda, what is the lambda? But SI system, 24 hours, 60 minutes, 60 seconds. 0.693 divided by 138 days divided by 24 hours divided by 3600. That is equal to, so you get a very small number. It is 1, 2, 3, 4, 5, 6, 7, 8. 5.812 into 10 to the power minus 8. I'll check it once again. 1, 2, 3, 4, 5, 6, 7, 8. Second to the power minus 1. This is lambda. Lambda is 5.812 into 10 to the power minus 8 per second. Okay, now convert that activity. What is the activity? Radioactivity. 5 millicurie. 5 millicurie. That is equal to 5 milli into 1 curie is 3.7 into 10 to the power 10 disintegrations per second, into 3.7 into 10 to the power 10 disintegrations per second, or becquerel, because 1 disintegration per second is called 1 becquerel. Hope you can see this. Yes, up to this, yes, you can see that. So 1 becquerel is 1 disintegration per second, so many becquerels. So that is the activity. Okay, that is correct. R is equal to 5 millicurie. 5 into 10 to the power minus 3 into 3.7 into 10 to the power 10. So this is used to convert curie to disintegrations per second. So now A is equal, activity R is equal to lambda n, which is minus dn by dt. R is minus dn by dt. dn by dt is minus lambda n. So minus dn by dt is plus lambda n. So R is equal to lambda n. Now what is the radioactivity? That is, shall I multiply this? 5 sevens are 35, 18.5, correct? 18.5 into 10 to the power, this is 7, is equal to lambda is 5.8 into 10, 812, 5.812 into 10 to the power minus 8 into number of atoms in the sample. This many number of atoms show this much of activity in disintegrations per second. Okay, now what is n? N is equal to 18.5 into 10 to the power 7 divided by 5.812 into 10 to the power minus 8. That is equal to, so I have to calculate this now. 18.5, my cable is getting twisted to my body. So 18.5, where is 18.5? Yeah, 18.5 into 10 to the power 7 divided by 5.812 into 10 to the power minus 8. So 18.5 divided by 5.812 is equal to 3.18 into 10 to the power 15 atoms. So many atoms in the sample. Now you know that Avogadro number of atoms will weigh how much? 210 gram. Here, polonium mass number. So Avogadro number of atoms will weigh 210 gram. What is the mass of these many atoms? That should be the answer, correct? So shall I do it here? I'll do it here. Avogadro number of atoms, 6.02 into 10 to the power 23 atoms weigh 210 gram kg, 10 to the power minus 3. 6.02 into 10 to the power 23, 6.023 we have. Okay, 6.023 into 10 to the power 23 atoms weigh 210 gram. What about this many number of atoms? 3.18 into 10 to the power 15 atoms weigh how much mass? These many atoms. So simple it is. Yeah, m is equal to, so you have to calculate this. That should be this answer. Let us see if we will get it or not. 210 into 3.18 210 into 3.18 is equal to divided by 6.023, that is equal to, we are getting it, 110.87, 49, that is 5 into 10 to the power 23 minus 23 minus 26, minus 26 plus 15, minus 11, right? No? So many, minus 11 kg, because I have converted everything to kg. Here it is in gram. If you want to put it in gram, multiply and divide by 1000, then so much of kg. Do you get minus 8? Multiply and divide by 1000 if you want to. So divided by 1000 into 10 to the power minus 3 kg, gram, right. This much of gram means into 10 to the power minus 3 kg, correct. So 110.875 into 10 to the power minus 11 kg, or 110.875 into 10 to the power minus 8 grams. So this is the mass of the sample. So you must have an idea of how this problem is carried on. First, you have to calculate from one data, that is lambda or half-life, you have to calculate lambda. Once you get lambda, you must know activity. If you know activity, you can calculate number of atoms in the sample. Once you get the number of atoms in the sample, mass is very easy because you have Avogadro number connection. Avogadro number weigh this much. What about this many number? So we got the answer, right? Shall we move on to the next problem? Yes, second one. Calculate the mass in gram of radium-226, whose activity is 1 curie. Calculate the activity of calculate the mass in gram of radium-226, whose activity is 1 curie, and half-life is 1620 years, and given Avogadro number. You see, actually this is the definition, right? What is 1 curie? 1 curie is the activity of 1 gram of radium. That is why it is taken as 1 curie, because it is the discovery of radium is the discovery of Marie Curie. So it is taken as a CGS system. Since it is a CGS system unit, 1 curie, we take 1 gram of radium. Activity of 1 gram of radium is 1 curie. So if this is 1 curie, same problem as the previous one, but let it be an experience for us. So first of all, you take half-life and calculate what is lambda. What is lambda? Lambda is equal to, you see the half-life of this, 1620 years, right? Half-life is equal to, lambda is equal to 0.693 by half-life, because period T is equal to 0.693 by lambda. So lambda is 0.693 by T half, that is equal to 0.693 divided by half-life. 1620 years, 1620 years, 365 days. Here you have a very big number. 365 days, 24 hours and 60 minutes into 60 seconds. Very large number. Let it be like this. We will calculate it at the end, because that gives 10 to the power minus something. So lambda is 0.693 divided by 1620 years, 365 days, 24 hours, 60 minutes, 60 seconds. That is lambda. What about activity of the sample? Activity of the sample is 1 curie. So activity is 1 curie, which is equal to 3.7 into 10 to the power 10 disintegration per second, or becquerel, right? BQ. So that is activity, has been converted into SI system. Then what? What next? So activity of a sample R, which is equal to minus dN by dt, is equal to lambda into N. Okay? Decay constant into number of atoms in the sample. Now 3.7 into 10 to the power 10 is equal to lambda. Lambda is 0.693 divided by 1620 years, 365 days, 24 hours, 60 minutes, 60 seconds, and into N. What is the number of atoms in the sample? Is equal to 3.7 into 10 to the power 10 into 1620 years, 365 days, 24 hours, 60 minutes into 60 seconds, 3600. 3.7 into 10 to the power 10, 1620, 365, 24, 60, 60. Everything is over. And 0.693. This becomes easy. Okay. So what is the number of atoms in the sample then? Which show that much of activity, 1 curie. So answer should be at least 1 gram, very close to 1 gram. Okay, we will do that. How much we get now? Yeah, 3.7 into 1620 into 365 days, 24 hours, 60 minutes into 60 seconds, 3600 is equal to this much divided by 0.693 again is equal to this much. So this is a very large number. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 2.73 10 to the power 12 atoms. This is the number of atoms in the sample. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 2 point. Do you have a decimal point after that? I think I have. Or shall I take it as only 36? 3.7 into, oh, here you have one more, 10 to the power 10 into 1620 into 365 into 24 into, I'll take it as 3.6 so that I can leave 100. So how much I get? 1, 2, 3, 4, 5, 6, 7, 8, 9. Yes, 12, correct. Into 10 to the power 10. So you have one more 10 to the power 10 here. Into 10 to the power 10. Please have a calculator and check along with me. Calculate along with me. Otherwise, it will be boring class. Just looking into this problem is a boring class. Yeah, 0.693. 0.693 is over. So how much now? Number of atoms in the sample? 2.73 into 10 to the power 22 atoms. Because we have a 10 to the power 10 here. Now how many, these many atoms will weigh how much? That is what you have to do. Now 6.023 into 10 to the power 6.023 into 10 to the power 23 atoms weigh how much? Radium 226 gram. We will put it in gram only. What about these many atoms? 2.73 into 10 to the power 22 atoms weigh how much? So you have to calculate the mass. Okay, 226 into 2.73, yeah, divided by 6.023, how much? That is equal to 102.43. okay, and here you have 10 to the power minus 1, because 23 minus 23, then you will get 10.2. Somewhere we have to check it. 10.2, it should be 1.02, right? 10.2 gram I get. I didn't convert it into kg. 226 gram I have taken. So these many number of atoms. 6.023 into 10 to the power 23 atoms weigh this much. I think we have gone wrong somewhere here in 10 to the powers. Okay, this is correct. Now we will check it again. Shall I write it this one like this? No, not that one. I have to write this one. I will check it like this, because so many powers will not be filled in the calculator. 0.693 here. Did I divide it by 0.693? Hope so. 3.7 and this is 1.62. I'll do it like this, 1.62, then 3.65 into, I'll rub this, 110 to the power we are missing. 3.7, 1.62 and 3.65, 2.4, sorry, well, let it be 24, no problem, 3.6. So that is equal to, so what I can do is, how much 10 to the power I have retained here? 3.7 as it is. Here 3, 10 to the power 3, because I have written only 1.62. 10 to the power 3, 10 to the power 2, 5 and 10 to the power 3, 10 to the power 8. 10 to the power 8. Correct? And this 10 to the power 10. Here 1.62, 10 to the power 3, 10 to the power 2, 5, 10 to the power 3, 8. into, that's what I have to do. Okay, what I'll get, that is equal to 10 to the power 8 into 10 to the power 10. Yes. Now you calculate this. 3.7 into 1.62 into 3.65 into 24 into 3.6, 1890, divided by 0.693. 3 is equal to 2727.6, 2727.6 into 10 to the power 18, that is equal to, so if I bring it here, 2.7276 into 10 to the power 21, because 3 places here and this 18, 21. So what did we write here? 2727. Where is it? Number of atoms in the sample. Yeah, 27. Yeah, where you have to substitute the mass. Yeah, 2 point. Here 2 point. This has to be. I'll rub this. 6.02 into 10 to the power 23 atoms weigh 226 gram. Okay, gram only. What about 2.7276 into 10 to the power 21 atoms weigh? Because we got 10.2, we should be 1.02 gram. Yeah, 226 into 2.7276 is equal to this much, divided by 6.02. You get 102.39, 102.39 into 10 to the power minus 2. Now you get it, 1.024 gram. Right, because we have not converted into 226 into kg, that is gram. So similar problem. Okay, we will move on to the next one. Yeah, find the activity of 1 gram of radium. This is a ulta problem now. You are asked to find out the activity now. Find the activity of 1 gram of radium whose half-life is 1620 years. So only the thing is, you have to 1 gram, in 1 gram how many atoms are there? It is exactly reverse problem, where number of atoms, mass is given 1 gram, find out the number of atoms, multiply to lambda, then you will get what the answer they want. That is activity. So do you want to find it out in Curie? Yes, you have to find it out in Curie. Okay, shall we start it? It is the mass. Find the activity of 1 gram of radium. Mass, it is 1 gram, 1 into 10 to the power, okay, 1 gram we will take. Now 226 gram contains Avogadro number of atoms, 6.023 into 10 to the power 23 atoms. Avogadro number of atoms, 226 gram weight, that much of mass contains Avogadro number of atoms. 1 mole. 1 mole of radium contains Avogadro number of atoms. What about 1 gram? I need not convert it into kg because this is also gram. If I convert it, then both will get cancelled. So this is the number of atoms. So we will calculate it. Right, 226 gram, 6.023 divided by 226. What is the answer? 0.0266 into 10 to the power 23 atoms. Okay, then what is activity? Radioactivity R is equal to lambda n. How do you calculate lambda? Lambda is 0.693 divided by half-life into n. So activity of radium is 0.693 divided by half-life, 1620 years, 365 days, 24 hours, 60 minutes, 60 seconds. Such a large number. into number of atoms. This one. Number of atoms is, so shall I change this? I will donate 3 zeros here. 26.6 into 10 to the power 20. Right? 1000 I will donate it to this. Not 1000, okay, if I donate it to 1000, then so 1, 2, 3, yes. 26.6 into 10 to the power 20. So what is activity? R is equal to so many becquerel, because it is in SI system. 0.693. Even though you have used gram here, it is equivalent. They have cancelled. So what is the 0.693 into 26.6 is equal to divided by 1620 divided by 365 divided by 24 divided by 3600. Oh, this is a very large, very small number with so many zeros. I don't find any 0.0s. Okay, 15. Okay, so shall I write one more step, because it doesn't get filled in my calculator, such a small number, because you get decimal point outside. Okay, you can do it like this. 0.693 into 26.6 into 10 to the power 20 divided by, I can write it as 1.620, 3.65 and 24, let it be like this. This 6 and 6, 36 and 10 to the power 2. This one. Okay, 10 to the power 2 here. Okay, I will write only 10 to the power 2. 36. What about here? 1.620, 10 to the power 3, 10 to the power 2, 10 to the power 5. What else? 10 to the power 5, here 2 zeros, 10 to the power 7. Correct? Here 10 to the power 3, 10 to the power 5, and I would consider 36, not 3.6, 10 to the power 7. So now I will divide. I think now my calculator can fill it. 0.693 into 26.6 is equal to divided by 1.620 divided by 3.65 24 36.00360 0.00360 into 10 to the power how much? See here, 20 minus 7, that is 13. This much of becquerel. It is not activity is not Curie, it is becquerel, because everything is in SI system. Now we want to convert it into Curie. It should be 1 Curie almost, right? 0.9768, because activity of 1 gram of radium itself is 1 Curie. So it should be 1 Curie. So what I can do? 1 Curie is 3.7 into 10 to the power 10 disintegrations, or 3.7 into 10 to the power 10 disintegration is 1 Curie. How much is this one? 3.7. So activity in Curie, 3.7 into 10 to the power 10 disintegrations per second is 1 Curie. What about this one? 0.00360 into 10 to the power 13 disintegrations per second is how much Curie? 3.7 into 10 to the power 10 is 1 Curie. 0.00360 into 10 to the power 13 is how much? Yes, 0.00360 divided by 3.7 is equal to 0.00097. But you have here 10 to the power minus 10 here. You have 10 to the power 3 remaining. 10 to the power 3 remaining means 1000 into. So what is 1000 into? You will get 0.973. 0.973 Curie. Yeah, 68 you have. 0.9729 I got. So that is the answer. So reverse calculation. So everywhere what you have to do is, if mass is given, find out how many number of atoms are there. A is equal to lambda n. If lambda is not given, from half-life you get lambda. Only the thing is long amount of calculation. Okay, next one. Yeah, this is a problem, a similar problem what you have worked out in the previous class, nuclear physics, but still we will work it out. Okay. A nuclear reactor develops nuclear energy at a rate of 2700 kilowatt. Yes, 27,000 kilowatt. So power is 27,000 kilowatt. So much of energy. That means power is 27 into 10 to the power 6. It is kilowatt. Joules per second, right? This one jumbled together. Watt is nothing but joules per second. So every second you have to produce 27 into 10 to the power 6 joules. How much amount of how many kgs of uranium 235 would be required for 500 hours of operation, right? Per second we will calculate first. Power is equal to 27 into 10 to the power 6 joules per second. Actually I should have given this as homework, but let it be. We will work it out. You work out together so that you will get some confidence, right? Where are we now? Yes, 200 million electron volt of energy is released per fission. Now convert this into joules. What is the energy per fission? Energy per fission. In one fission how much energy you get? Is equal to 200 million electron volt, that is equal to 1.602 into 10 to the power minus 19 joules. This is for one fission, but we need this much of energy in 1 second. That means how many fissions are required? Therefore number of fissions required is equal to, so we need this much energy, 27 into 10 to the power 6 divided by 200 into 1.602 into 10 to the power minus 13, right? 200 into 1.602, 6 and minus 19, minus 13. So much energy. So how many fissions will make this much of energy? Correct? Yeah. So how many fissions are required? So many atoms should be there in the material, right? So that in order to produce that much of total energy. So I can see this calculator at all. Yeah, 27 divided by 200, 27 divided by 200 is equal to, and divided by 1.602, that is equal to 0.008426. My calculator shows that much of value, I don't know from your side, 0.8426 into 10 to the power 19 fissions. That means so many atoms, because every atom undergoes once one fission, right? And then it yields 200 million electron volt of energy. So first you take energy per fission, convert it into joules. For getting so much of joules of energy, how many fissions are required? So this many number of atoms or fissions. Now how much mass of uranium is required now? 235. Here we have atoms, right? Avogadro number of atoms, 6.02 into 10 to the power 23 atoms. They weigh 235 gram. Okay, I will convert it into kg. Then these many atoms weigh how much kg? 0.08426. 0.08426 into 10 to the power 19 atoms. Because we need this many atoms per second. Remember, everything is under second, per second. So these many atoms per second need how much of mass per second? Then finally to 500 hours. That we will do later. So these many atoms weigh 235 gram. These many atoms weigh how much gram? Again calculator. Yes. You will understand these problems now, but working out it in the examination is a different task, because you will have so much of pressure. Under pressure you have to do that. Okay, 235 into 0.08426 equal to, divided by 6.02, 3.289. 3.289 into 10 to the power. So this is the mass required, right? Mass, yes, mass. This much at atoms weigh this much. This many atoms weigh how much? 10 to the power minus 26 here, plus 19, minus 7 kg. Right? This is per second. That we have left everywhere. This much of mass is required every second. So what is the mass required for 500 hours? Mass required for 500 hours. Okay, shall I write it here? Today I have to adjust with both. Mass required for 500 hours. M is equal to, this is per second, 3.289 into 10 to the power minus 7 kg into 500 hours, 60 seconds, 60 minutes, 60 seconds is equal to 3.829, 289 into 500 into 60 into 60. That comes to, we are getting the answer. You have so many zeros. 5920 point, okay, 0 into 10 to the power minus 7. So will it come to 1, 2, 3, 4, 5, 6, 7, exactly 0.592, of course there is 3 gram, kg, yes. That is the answer. So same type of problem, just for a revision I got it here. So this is the way in which, and we solve the problem. And in entrance exam regarding to radioactivity and nuclear physics, you have some problems wherein you need not go for such a long calculation, because you will be given the values in such a way that you will get the answer immediately. Only the thing is, you should have the flow of problem very firmly fixed in your brain. What you have to do, calculate the mass, calculate the number of atoms, and mix it with the Vivekananda number or something like decay constant. All these formulas will be very intact. Then only you can solve the problem. So next, in 1 or 2 classes, I will send you the material. We will solve an entrance exam problem, so that this becomes easier, because that flow chart becomes very easy once you solve the entrance exam problem. How to solve this, that idea of solving becomes very firm. Here of course you need to wait for the answer, because it needs more calculation. In entrance exam you need not wait for the answer, because calculations are easy, you will get the answer. So you see that, so see those entrance exam problems, how easy they are. You can do them, right? So try to follow it up along with this. Then we will have some heavier examples for entrance exam later, so that if you have some touch on the entrance exam problems, it becomes easier later to continue it. Okay, with this I will stop today's class. Thanks for watching my class. We will meet in the next class with the entrance exam problems. Thank you.